Let's begin. So, hello everyone. The title of my presentation is Multimodal Hand Pose Enhancement for Sign Language. I'm going to be presenting the work that I've been carrying out with Laia Tarrés and Xavi Giró as part of the course called Introduction to Research. So this is the outline of my presentation. I will begin by introducing a little bit sign language and some prior works that I built upon, which are how to sign and body to hand. Then I will discuss some ways in which we can represent sign language data. And after that, I will go over the exploration that I carried out this past few months to try to improve the current hand pose estimation systems, which is the main topic of my presentation. So sign language, to get an overview, sign language is a family of languages that are mainly spoken by the deaf community, over 450 million people worldwide. An important difference between the text that we are accustomed to and sign language is that text has a discrete representation, whereas sign language has a continuous representation. This is the main reason why it is hard to develop sign language communication technologies. Recently, there have been some interesting attempts at processing sign language with deep learning. We all know that deep learning combined with large amounts of data works pretty well. However, it is quite hard to obtain sign language data due to the multimodal nature of the problem. So despite this difficulty, new data sets, such as how to sign, have been proposed that address this lack of data. Now let's take a closer look at the how to sign dataset. We make extensive use of this how to sign dataset, which was proposed by Duarte and others here in UPC in 2021. How to Sign is a large-scale collection of American Sign Language videos with sentence-level alignment for over 35,000 sentences. We used annotations for category labels, for text annotations, and automatically extracted to the key points. The second building block of our investigation is a recent method called body to hands. We decided to explore the application of this novel body to hands method, which was initially designed for conversational settings, and we transferred it to the domain of sign language with the aim of improving the current hand pose estimation systems. So body to hands is a deep learning method, which was designed for estimating hand poses in conversational situations. We thought that maybe body to hands could be applied to the domain of sign language. So body to hands is a generative adversarial network with a fully convolutional one-dimensional encoder-decoder for the generator and a fully convolutional discriminator. It receives as input the body poses as 3D key points, and it outputs realistic hand poses. It also allows the option of using image feature vectors as input. It is a non-causal system because the entire sequence of hand poses is fed to the model at once. An important part of our exploration is related to deciding how to represent sign language data. This is a challenge in and of itself that we needed to address. So as I said before, sign language doesn't have or does not admit a discrete representation, but at the same time, directly processing sign language data is quite difficult because it is very resource intensive and very time consuming. So for this reason, if we were to use raw video data, the sign language processing systems would need to learn to ignore non-relevant features such as background or clothing, and we need to focus just on the relevant features such as the hand pose or the facial features. This would add another difficulty on the already difficult task of sign language processing. So for this reason, in most cases, what we do is we extract key points from the video and then process these key points directly. These key points correspond to the joins and other points that are relevant for the topic for understanding the signer's pose. The advantage of key points is that they make systems more robust to changes in background and variability among signers. So in the case of how to sign, we extract these 2D key points are extracted with open pose. Okay, this is unfortunate because for some reason today I'm having trouble rendering this. Well, anyway, we use open pose to extract 2D coordinates. However, this 2D representation is sensitive to occlusions and changes in angle. So if you can see at some moment, the speaker puts one hand in front of the other, and which is an occlusion. And in this case, we've got very noisy 2D key points. Since 2D key points are not enough, what we usually do is lift them to 3D, which basically means obtaining a reasonable Z coordinate from the X and Y coordinates. So notice how the animation on the right, there can be some non-realistic hand poses, such as this one here. This motivates the need for systems that can correct these noisy poses that are produced after the 3D lifting. If these inadequate poses are not addressed, our deep learning systems will suffer. Which leads us to the main motivation for our work. We leverage body to hands to improve the current hand pose estimation systems for the domain of sign language. And for this, we use RGB videos and key point sequences. As I said, 2D key points are not suitable or ideal, so they are lifted to 3D. To do this, we used an off-the-shelf method proposed by Zelinka and others. We also defined a kinematic tree, which allows us to define how joints are related to each other. Although 3D key points are more robust than 2D, they still have some problems. They are not robust against changes in scale and length of the speaker's limbs. For example, a very tall signer and a very short signer could be saying exactly the same thing, but since their arms and hands are very different in size, their 3D skeletal representation would be quite different. We would want that, since they are saying more or less the same thing, that their representation would be more or less equal. To mitigate this issue, we convert the data from Cartesian coordinates to a rotational representation. So first, we obtain the axis angle representation, and then we compute the R6D representation. So to obtain the axis angle representation, what we do is the following. Given a pair of bones, let's say V and U, we compute the axis A, around which we can rotate V to put it on the direction of U. Moreover, we compute an angle theta, which unfortunately is not rendering today. And this angle theta indicates how much we rotate around around axis A to go from direction V to direction U. We follow this process for each pair of bones by traversing the kinematic tree. And once we have this axis angle representation, we obtain the R6D representation by computing the rotation matrix and then taking the first two vectors of this matrix, thus obtaining a vector with 6 components. Okay, so once we are clear on how to represent the data, we can begin transferring body to hands to sign language. Our first attempt was to directly train body to hands on sign language data from the how to sign dataset. We also explored the possibility of conditioning the model's output on image features, as well as on sentence text embeddings. Here in the image on the right shows how this approach did not really manage to generate any meaningful poses. On the left, we got the generated poses, and on the right, we got the original ones. So as you can see, the model falls on what is known as model collapse, and it always predicts the median pose. This indicates that body to hands cannot be used directly as an off-the-shelf method for sign language. Then we turned to the task of unmasking some of the signer's fingers, given the rest of the fingers. So this task differs from the previous setting in that here we also use as input the hands, while initially body to hands only used the arms. This unmasking task allows us to determine the capacity of the model, the capacity that the model has for filling in the missing fingers and generate meaningful poses. We unmask fingers sequentially, starting from the left pinky finger up to the thumb. We found that the model can properly unmask 1 or 2 fingers and generate quality, let's say quality representation, such as this. Here we mask the pinky, and as you can see, the generated finger looks quite realistic. However, as you can see on the right, the model struggles to produce any meaningful poses when it must reconstruct an entire hand. So this leads us to the conclusion that the model is not suitable for generating new hand poses. However, it also showed that it could potentially be used to enhance pre-existing hand poses. And now, let's dive into the main task of our work, which was hand pose enhancement. On this slide, we can see again the typical pipeline for obtaining 3D poses that I showed before. As I said, sometimes the obtained poses can be quite noisy and inadequate. So we explored the idea of using the model proposed in Value2Hands to enhance the filter the noisy poses which are produced by the key point obtention systems. For this task, we use as input the arms as well as the hand poses, and we force the model to reconstruct the noisy pseudo-ground truth labels with an L1 reconstruction loss. Since the generator is an encoder-decoder model, its bottleneck has a regularizing effect that forces the model to remove the most prominent noise, or the most clear noise in the input poses. So, for instance, if you look at this image before, you can see here that there are some quite noisy poses. However, if we look at the enhanced output, you can see here that now the pose for the left hand does not contain anatomically impossible poses, which is what we were looking for. A quantitative evaluation of the task was not directly available because we are not directly aiming at reconstructing the hand poses. For this reason, we first perform a qualitative evaluation of the results. And overall, we found that the model manages to remove clearly wrong poses, such as the one here on the right. However, sometimes it also removes small but meaningful gestures, such as those gestures that a signer makes when she's spelling out the word. Since asking for feedback directly from sign language speakers was not an option for us, we decided to evaluate the model against a surrogate task. We chose to evaluate our method against the task of topic detection due to its simplicity and because category labels are available in the How to Sign dataset. The How to Sign dataset provides 10 topic annotations, and by default, this dataset contains key point and text annotations at sentence level, which means that data is partitioned sentence by sentence, as opposed to video by video. However, sentences can be grouped and ordered based on their video of origin to obtain video level data. Later, we will discuss whether to use sentence level or video level data. For the topic detection task, we encountered 2 different kinds of data. Therefore, we need 2 different kinds of models. For textual data, we fed the text into a pre-trained transformer, a BERT transformer, which produced rich textual embeddings, as you can see in this illustration. Then we use these embeddings as input to a multi-layer perceptron classifier that we can train. Since there is no method available yet for directly processing sign language data and obtaining embeddings as we would do for text, we needed a model that is capable of dealing with sequential data. We chose the more traditional LSTM due to its simplicity. So what we do is we feed a sequence of key points to the LSTM, and then we use the last hidden state as input to our trainable classifier. So to check if sentence-level data is enough for classification, we trained the model to classify textual sentence-level data. So as you can see on the plot, this classifier was not able to learn any meaningful representation, and its validation accuracy does not improve. Notice here that the accuracy stays around 23%, which is the prevalence of the majority class in the dataset. This implies that the model was not able to obtain meaningful representations with sentence-level data. So we concluded that we had to group the data at video level for having rich enough sequences that we can deal with. So now, next, to make sure that the topic detection task is actually solvable, we first utilize textual data before using sign language data. We leverage state-of-the-art NLP techniques, as I showed previously. So with textual data at video level, and after some hyperparameter tuning, we managed to obtain a validation accuracy of about 77%, which means that the topic detection task can be solved. Since the topic detection task, we know that now that it's solvable, we turn to the task of using topic detection using sign language data. Before using data in the rotational representation, we wanted to prove that 2D key points are not really suitable for sign language processing, as we said in the beginning. And as we expected, 2D data does not allow us to successfully classify. What's more, it does not even allow to overfit the training data, the training set. Instead, the classifier falls to predict the most frequent class, even in the case of training data. And finally, we compared the classification results on the enhanced poses against the original noisy ones. So on the plot, the green line corresponds to non-filtered data, whereas the blue line corresponds to filtered data. Although in the initial epochs, the validation accuracy is somewhat higher, we found no significant difference in performance between using the two types of data. It is true, however, that non-filtered data allows overfitting the training set more easily, as you can see with this green line. This lack of difference in performance could be due to a lack of capacity on the LSTM part, which might not be adequate to solve this kind of problem. We believe that a more powerful architecture would be needed to really tackle this problem effectively. Finally, I will give an overview of what I've been presenting. So first, we decided to focus on body to hands, which was a method initially proposed for hand pose estimation in conversational settings, and we tried to transfer it to the domain of sign language. We tried to directly apply it as an off-the-shelf method on sign language data, and we found that body to hands is not adequate for our purposes as an off-the-shelf method. However, when we encountered then some of the limits of body to hands, while at the same time realizing that it could be used for improving the current hand pose estimation systems that we are using. Then we show some qualitatively promising results in hand pose enhancement. And although no gain was made in terms of validation accuracy on the topic detection task with enhanced poses as opposed to non-enhanced poses, we believe that this could be due to the fact that an LSTM is not suitable for this task. And a more specific architecture, such as sign language transformer, would be ideal to really come to a conclusion about this, about whether enhanced poses really improve this topic detection task or not. In the future, I intend to continue investigating this topic, thanks to a collaboration grant that I received within the framework of my bachelor's thesis at UPC. And that's all. I hope my explanations were clear, and I'll be glad to answer any questions.
Thank you very much. Let me stop the recording.